Ladies and gentlemen, I am very pleased that I can have a talk today about my personal effort in the area of observational astronomy, effort to achieve the widest possible field of view, but on a quite limited budget. That means without the luxury of huge amount of money available, but as a matter with a budget which is quite limited. So what I would like to talk today, why would we even try to achieve large field of view? We will discuss some dilemma between field of view and resolution. We will discuss a few professional wide field telescopes and amateur wide field telescopes. We will touch some issues which arise from data processing of very large fields of view. And at the last subchapter, I will present some results from the setup. So, while large field of view is very simple, as we invest time and money to the equipment, and the time is very, very important for amateurs who just can't tell the boss, sorry, it was very interesting transit last night, I will not appear in work today. So after the night they have to wake up and go to the regular daytime job. It's only natural that we want that the revert is maximized. We have maximum available data from our observation. I start with a few examples. The quadruple star system, Czech V343, was discovered in 2012, and as you can see, it was in edge over field of view, and compared to field of view used those time, which are marked by red rectangles. If I did not experiment with wide field telescope this time, I would definitely miss the star. The same is valid also for cataclysmic variable Czech V404. It is also located out of typical field of view. And if I looked at our currently 6 registered discovered quadruple star systems, 5 of the 6 are located outside of the typical field of view, and this one in particular would be even missed if I did not upgrade my telescope in 2015 to even bigger field of view. So this is why we want to achieve really wide field of view. Getting a wide field is a race against nature, because optics, it's a property of any optics to provide worse and worse image if you are farther and farther from optical axis. The image on the right is really the parabolic mirror, and the green lines are parallel to the optical axis and are perfectly focused. The red lines are definitely not properly focused.
This is an extreme case, because in reality the diameter of the mirror relative to focal length would be much smaller, and also the angle would be much smaller, because the field of view here is about 25 degrees, which is really much more than is typical. Those two images originate from a famous book, Universe, from Grigar, Horsky, and Mayer. And I don't know what was the source of the image, because only archive of Prague Planetarium was mentioned. And you can see the stars perfectly shaped like small comets. This is a demonstration of the aberration. Also, refractors have limited field of view. This is a very small refractor which advertises itself as a ED refractor, and you can see that when you increase the sensor, the quality of image close to the edge rapidly decreases and is beyond usable very soon. Very commonly available wide-field optics are photographic lenses. And photographic lenses are designed for sensors, APS or full-frame sensors. But the disadvantage of photographic lenses is that they have limited diameter, only typically a few centimeters. Focal length is also very limited. It's tens of centimeters. And what you get is an image which is wide field, but typically contains only bright stars because of small diameter, and suffer from very small angular resolution because of very short focal length. If we compare projects which use photographic lenses like Assassin, or which use lenses which are not photographic but custom built, but the characteristics are very, very similar to photographic lenses, is TESS itself, which was mentioned here. The M31 Andromeda Galaxy is image from Assassin, from TESS, and from our ground-based observation. And if I zoom into detail, you can clearly see what's the disadvantage of the 24-degree field of view of TESS telescope. The number of stars you can distinguish is really very small. By the way, it's beautiful, visible on those images that Assassin and our ground observation use equatorial system, while TESS use ecliptical system, so the orientation of the pixel axis are different. So our target is not only to get wide field of view as possible, but also to get as good angular resolution as possible, or should be seeing limited. That means a couple of arc seconds, because if we get some difficult target which is pretty close to another bright star, and in fact another star is also eclipsing variable, then only if you have good enough angular resolution, we can get good enough data. How it works. So let's start with professional and some overview of professional and amateur wide field telescopes. Yeah, I have a bit apologize for the next. Oh, I believe the batteries are close to, because this slide is a bit out of topic. This slide I could not resist to put it here. It shows the Vera Rubin telescope, formerly last synoptic survey telescope, but it's an engineering marvel. It's an excellent piece of engineering and an extremely beautiful design of a wide field telescope with field of view 3.5 degrees and with a diameter of 8.4 meters. It's consists of 3 mirrors. 2 of them are made on a single substrate. So it's really wonderful, but only it's just, as I said, I could not resist to put it here because it's one of a kind. It's not ready yet. It's still in construction. And the optical corrector, we will mention optical correctors later, starts with 1.5 meter diameter lens. So it's really, even in professionals, it's one of kind, as I said. A little bit down to earth wide field telescope is available. It is commercially available. It's, for instance, ASA 40 centimeter astrograph with less than 1 meter focal length, and which provides sampling less than 1 arc second per pixel. And the field of view is a beautiful 190 minutes by 140 minutes, which is really, really almost as wide as Vera Rubin telescope, of course, with much smaller mirror. There is an issue. Issue is that the cost of one optical tube, just one tube, starts at the cost of luxury car here in Czechia. So if you come home and say, "Sorry, I did not brought a new car, but I have a new telescope," you probably could have a problem. So let's go even lower. For instance, yeah, those images are images taken with this setup. That's the 150 megapixel camera, and just look at the field of view. Everybody knows how big is the Orion Nebula, and this field of view is perfectly covered to better than 1 arc second per pixel resolution. Yeah, that's really nice. I have to mention the wide field reflectors because astro imagers, astrophotographers use wide field reflectors very often, but reflectors have problems similar to photographic lenses. They are typically small with short focal length, and they are expensive because they consist of a lot of lenses. Some of those lenses are made from rare glasses with low dispersion. So it is really not very suitable for this kind of telescopes are not very suitable to build wide field system for amateurs. The Holy Grail is a corrected Newtonian telescope. It's the poor man on a title is in quotes because compared to ASA astrograph or other telescope, it's cheap, but still when corrector costs a couple of thousand of euros, it's not that cheap, but it's the best price performance ratio we can get. The plus of the corrected Newtonian is that when we use standard Newtonian with parabolic mirror, a lot of companies do the optics, and we can choose high quality mirror for pretty low cost. Also, the optical corrector necessary it's not necessary to build the corrector and the mirror together. Correctors are available off the shelf and can be combined with any mirror or almost any mirror if you have some basic properties like f ratio and minimal size, then we can combine it with a corrector. If we try to build a wide field scope, the aberrations and correctors are not the only obstacles we can meet. Field of view could be limited by other pieces of the design. For instance, you can have too small tube, and the tube will provide vignetting and limit the field of view. You have too small secondary mirror. You have too small focuser, filter wheel, and of course, if you need wide field of view, you need a proper camera with a big enough sensor because small sensor also naturally limits field of view. Even if when we discuss focusers, we will deal with the standards like 2-inch focusers, which are typical, and vast majority of amateurs use telescopes using this standard, but it's only about 5 centimeters, and it's quite limiting. But still, the corrector can be of different design, and what you can see on the image on the right are two correctors with the same optics, but just different mechanics. And as you can see, the output element of much bigger diameter allows for much wider field of view. But there are also other standards like 3-inch diameter, which is more and more common, or still pretty rare 4-inch diameter corrector, which are now available. The corrector design is virtually all correctors are the same. Comma correctors are the same. Is a 3-lens design. And the design really is very similar to what we see on Vera Rubin telescope, because what's the purpose of a corrector? We have some aberration, and we need to correct it. So we need some degrees of freedom, which we can use to provide different aberration, opposite sign aberration, and it will be eliminated. So we add some refraction elements, more surfaces on which the light bends, and then we can design it the way we need. Some exception is a American Tel Aviv paracord, which does not use 3 lenses, but 4 lenses in 2 groups, but this is maybe an important detail. So to introduce to my experience, my path to wide field, I went through 3 iterations of a telescope. First was the off-the-shelf Newtonian, and it was used to discover first interesting star and show me that using wide field is really could be rewarding. It could lead to interesting discoveries. The second iteration, which really provide wide field of view, and now the new one, the third iteration of the telescope. So the first one used pretty common components which could be bought elsewhere, with very few modifications like bigger secondary mirror and so on. The second one was custom built. It does not contain any commercial available or pre-built system. The third one replaces some important pieces and make the field even wider. For instance, this is some component like the 4-inch corrector, the focuser, which compared to which the biggest camera looks like a small one, and here are the field of view compared from 70, 90 to 116 degrees, just to have some idea of what does it mean. I just copied and pasted the moon on the one field of view, so you can count almost 4 moon over the field of view. But as I said, the wide field of view is not at the cost of resolution. On the right, there is a DSS survey, digitized sky survey, and on the left is actual image from a telescope, and you can see the angular resolution is pretty comparable. So regarding wide field data processing, it's only natural. If you have very large images, you need fast computer and you need a lot of memory. Typical 64 gigabytes of memory is minimum, and 96 is typically big enough. Also, the used software pipeline can use any CPU available. So the more CPU you put in the processing, the faster the processing is. Very important part of data processing is modeling of field curvature, because the correctors provide sharp images of stars over the field of view, but move the stars from ideal tangential projection. So you need to model the deformation and count it with further processing, because if you try to match star, which should be here, but is 8, 10, 12 pixels shifted, you probably cannot match such star with a catalog. Yeah, that's the and on the very end, a few results. I try to summarize some results from the wide field setup. The observation is always done in fields. So I start with a field and then observe it for multiple nights, possibly many tens of nights, and to mine everything interesting in the field of view. And if there is really something interesting in the field of view, then the field is observed through the years and years to get a very long data set. So it's with the latest version of the wide field telescope, it's not an exception to have over 200 variable stars in single field of view. Okay, and for the last couple of slides, It's like double eclipsing quadruple star system. 6 total appeared in those fields. Here are some examples with O minus, how the folded light curve looks like, and ETV diagram. Sometimes the ETV diagrams are very, very interesting. I mentioned the cataclysmic variable. It's only one, but despite it's only one, so this is the cataclysmic variable light curve, the folded light curve, and also some ETV diagram. Flare stars, star which shows some flares, some occasional brightening, and here are also a few examples of star. Some of them are only flare stars. Some of them show some periodic changes, and some of them are also eclipsing binaries. Stars with ETV changes, there are a lot of them, so the list is pretty long, and ETV changes are shown here of very, very short example. Eccentric stars, there are also more than few of them, and also some examples of how eccentric stars say. So the number of possibly interesting objects are pretty big, which appeared in those wide field of view. So that's why I tried to show you why it could be important. Thank you.
Thank you very much for a nice presentation. It's really impressive. And do you have any questions or notes? And also for the online participants, you can ask on the chat or try unmute your microphone. Maybe I have one question. Usually, how long does it take to do the photometry of your field? Like how long in the minutes?
Yeah, it depends on which part of the sky the field appears, because of course field in winter constellations could be observed for 6-7 hours uninterrupted. Fields on spring parts of the sky could be observed by 3 or 4 hours maximum.
I think to do the photometry, not the observing, like how many minutes to do the photometry it takes.
Process the fields.
Yeah, the process.
Yeah, sorry, I did. Sorry, my apologies. I missed the question. Yeah, with my 16-core CPU, it's about it depends on the number of images, if it's say 200 or 600, but it's tens of minutes. So it could be 15 minutes, it could be 20, 30 minutes for very, very large field of view.
Okay, thank you. And any questions or comments? And on the online? No? Okay. So thank you very much, Pavel, for your talk.